So let's take a look at our first algorithm for doing page replacement. This is going to be just FIFO. So this is kind of the thing we always start with, right? This is kind of the simplest method, right? Basically, have something like a queue that stores all the different pages that are available. And this queue will have a fixed size, of course. We'll jump down to the diagram in a second, but for now, I just picture, right, you have a queue. This queue has a certain size, right? And the size represents, these are how many pages I can have in memory at a time. And as I add new pages, I add to the back of the queue. And then when I need to basically pick a victim, I throw out the page in front, right? And I keep on kind of cycling through things. Note that the pages that are going to be available, right, are basically based on the order that they come in, right? So as pages come in, right, they take their place in the queue, they're allowed to stick around for a little bit, and eventually they get kicked out. So the order that I put things in, right, really influences the pages that are in the queue at any particular time. So let's take a look at a little example here. So first thing I have here is basically a reference string, right? So this is what I'm going to benchmark on. So we're going to start basically tracing the algorithm and also figure out how many page faults occurs. So first thing, right, is I have a 7, right? That's actually going to be a page fault. I'll put a little mark here. So that gets added to my queue, right? First thing is done right there. Then I get a 5, another page fault. Add the 5 to the queue. Another 9, right? And the page fault, add that to the queue. Then I get another 9, not a page fault because it's already there. That's fine, the queue stays the same. Then I get a 6, right? When I have a 6, that's going to be another page fault. And in this case, right, I basically am going to cycle my queue, right? So my 7 gets, which is the thing that was there first, right? That gets thrown out, and then the 6 gets added to the end of it. Then we do a 5, right? 5 is not a page fault because it's already there. The next one up is going to be a 2. 2 is going to trigger a page fault because it's not there, right? So in this case, the 5 gets cycled out, right? Notice that even though 5 was just used, because it was added to the queue way back over here, it's going to go ahead and be cycled out. So we get another page fault there. Then we go to 7, right? Another page fault, throw out the 9. Go to the 4, another page fault, throw out the 4, throw out the 6. Then we have 2, 7, 4. Then we have another, we access 1, right? That's another page fault, throw out the 2. So at the end of the day, right, we have this. So we have 7, 4, and 1 are the things in my queue. And then I have 8 page faults that occur. So not so good. All right, so that's kind of our basic algorithm. So first off for you guys is, what is the best possible ordering for this method? So this is the kind of our FIFO page replacement. What is the best possible input stream that I could have? Maybe take 1 second to think about that. So in this case, probably the easiest thing is going to be to have sort of sorted input, right? So if I have something that looks like this, like I'm just going to read kind of from the example up here, but I have something like 1, 2, 4, 5, 5, 6. 7, 7, 9, 9. If I have something that's ordered like that, then it's like, well, I'm going to have things just when I need them. All right, so that would be kind of the best kind of input, right? Everything's kind of grouped together. I can do it all in one shot. Second question here, what is the worst possible ordering for this method? Take 1 second to think about that. So the worst case here is probably going to be something it's like, well, it's going to be cyclic. I'll go ahead and draw those picture for you guys. So if I have this, then I have an issue. Because basically what happens is my queue can only contain 3 things at a time. So it's like, well, I'll have, 2, 3, 4, right? And I'll have just kicked out 1, and the next thing I need to load in is 1, right? So it's like, basically I never get a chance to reuse something that's already there because my cycle, right, is kind of 1 larger than the size of the queue. So as I'm, about to use something, right, that's when I throw it out. And it keeps on happening again and again and again, and I have basically a page fault every time. So something like that would be, the worst case. Now, as an interesting note here, and we won't spend too much time on it, FIFO is one of the algorithms that sometimes when we increase the size of the buffer, right, when we say, oh, I can store more pages, we actually get a decrease in performance. And that's not something we typically expect, right? Normally we'd expect that if I increase the number of pages an algorithm can store, well, then its performance is going to increase, right? Then I'm going to have fewer page faults. Well, that's not actually the case for FIFO. So let's take a look at that a little bit on the next slide. This is called Baladi's anomaly. So here, right, this is something that's kind of specific to FIFO. Well, some of the algorithms have this as well, right? In general, what we want to is basically avoid this. Baladi's anomaly is basically to say that sometimes when we increase the number of allowed pages, the number of page faults increases, right? So performance goes down, right? And this is an anomaly because it's this strange issue. So here's kind of a sequence here, right? I have kind of outlined for you guys. So I have this 1, 2, 3, 4, 1. This sequence is kind of very specially constructed. It's coming from the textbook. So there's 12 accesses that occur there. Okay, so keep that in mind. I have this. Now, what you could imagine doing, right, is basically benchmarking this and saying, okay, you know what, I'm going to run this in terms of the algorithm, right, for a certain kind of size or a certain number of pages, right, that I can catch, right, and I can see how well it performs. And that's what happens basically over here in this diagram. So in this diagram, you can basically see that we're starting at, for 1, right? So let's say I have the algorithm running and I'm allowed to keep 1 page at a time. Well, that means I'll have 12 page faults. Makes sense. I mean, if you have only one space, of course you're gonna have a fault every time. Then I go to 2, right? And 2, right, doesn't really help things, right? I still have 12 page faults. Then I go to storing 3 pages. All of a sudden I jump down. Right now I have only 9 page faults. And then right, I go to 4, and when I do 4, I jump back up to 10 page faults. Right, so this is my anomaly here, right? So here where I've gone from storing 3 pages to storing 4 pages, and when I did that, I actually made my performance worse, right? I have kind of one less, or one additional page fault that I need to take care of. So this is kind of our anomalous area, right? Is this thing right over here. So this is kind of a little bit of a tricky thing. If you're interested, you can actually go out and read those kind of technical papers to describe this. Overall, some about what's happening is that this is kind of relating to the idea of like if we have a cycle, right? So a worst case thing that could happen. Your cycle kind of length, right, is dependent upon basically the size of your array, right? The size of your buffer. And so if you kind of vary, if you kind of have if you vary your size of your buffer, right? Sometimes you'll catch a little sequence there where that little sequence basically you're gonna throw away something that you do actually want. So it's a little bit problematic. For now, don't worry too much about why this occurs. More just know that it can occur specifically with respect to FIFO, right? So this is a FIFO issue.